power levers, okay, because that's where we finished yesterday on Friday. We'll go through those again, a bit of recap maybe towards the end of the day. Okay, anybody got any questions about any subjects we covered on Thursday and Friday? If, make a note and we can go through those again later today. Okay, right, so we're going to look at power lever positions and types of levers and controls, of single and dual, and what happens when you move them. Hopefully make a bit of sense as well. So power lever positions, turboprop engines have essentially two types of control system. Strange enough, a single lever control, okay, which will incorporate HP cock and a few other bits and pieces, and it makes it far easier. Just change my pen there. You see there, one lever takes the effort away from the pilot. That makes it a bit easier to work with. So that will include the propeller control as well as the main throttle. Most of the common ones though, you can just see the picture here, you have two throttle type levers, depends on the twin engine, etc. This is the basic examples. One will be for your engine, one will be for the PCU, the propeller control unit. So let's look at the single lever controls first. So a turboprop engine of the direct drive type. Now we've not done module 15, we've sort of briefly mentioned that last week. We speak about a direct drive, a fixed turbine, and we also speak about what's called a free turbine. Now remember, just to recap, a fixed turbine is a spool, an engine, which is a compressor, a shaft, and a turbine, which is actually mechanically coupled to the gearbox. So for a free turbine, it's only the gas coming out the back of one of the other turbines, in this case HP, which will spin it. So in a fixed turbine, you tend to find we might have a single lever control. Okay, where both the fuel control unit, your fuel pump on the engine, and the propeller control unit is on one simple lever. Makes it far easier for the pilot to work. He just goes forward and backwards, and it all works happily, providing the engineers have set it up properly. Yeah, you keep it maintained. So basically, you get your throttle lever, forward movement of the power lever, your throttle lever. It increases the fuel flow to your engine and also selects the higher RPM on the PCU spring. Okay. So higher RPM, in other words, we're going to have a small angle of attack. Okay, so allow that higher RPM. Maximum RPM of the engine is governed by the propeller control unit. So you've got your fuel pumping your engine. Yes, that does the power, the fuel and the power of the engine. But on the propeller control unit, that is governed by a little governor. Remember, I showed you the weight last week, which will set, if it's sensing going too fast, it will decrease the amount of fuel going to it, and so on. In other words, it will change or increase the gap of the angle for the propeller. So although the engine is controlling, this lever is also, through a governor attached to your CSU, is controlling the angle of the propeller to match the power of the engine. So to make sure the propeller isn't going too fast, or likewise, it's not going too slow. Now we can do that is by changing the angle of attack. So should the maximum RPM rise to a predetermined level, the fuel control unit will take over and inhibit further rise of RPM. So should it get to a certain point, then the engine pump will say, wait a minute, that's too fast. It will then limit the amount of fuel in that as well. So they're working together, the propeller control unit and the FCU, with the governors controlling the fuel on the engine, work together to make sure they're all working in harmony. Now the propeller can be feathered manually during engine failure or shut down by the HP cock, your high pressure shut-off valve, to a feather position. So if you bring the power lever back the way to idle, because remember, we can only go in feather when we're at a slow engine speed. Well, if we cut off the engine, in fact, we've lost oil pressure. If we lost oil pressure, then the big spring takes over, pushes it into feather position, and that's ready to go. Okay. So we've got what's called control interconnection. In other words, two things working together. With the HP cock, ensures that the fuel flow to the engine, or the burners, where the fuel comes out inside the engine, gets shut off, because we don't want fuel going to an engine when it's shut down, because the engine will be very hot. You're speaking about 2000 degrees Celsius inside a combustion chamber. Well, if the engine's not spinning, and you keep adding fuel into there, you'll have a big ball of fire, which is not very good, obviously. That prevents the engine from overheating by trying to supply power to the blades in the feather position. Okay. So we shut off the fuel, basically. Now, throughout the movement of the power lever, from idle's at the lowest position, to maximum, the maximum power. The fuel flow will increase incrementally with that movement. Now, all movements, especially with a propeller engine, and especially a turboprop, it should be nice and smooth all the way up and nice and smooth all the way back. Not just sudden back and forward or up and down. It should be nice and smooth all the way. Providing you do that, it will work nice and smoothly. The propeller, though, is not controlled incrementally. So as we put the power lever up, the engine will increase power incrementally, as in stages, but propeller is sensing what's happening to the engine, and it's waiting to sense a speed, and then it will decide what angle of attack for the propeller will be. So initial movement of the power lever increases fuel flow only. There's no effect on the propeller control unit. So initially, if you're from idle on your engine, yes, the fuel goes to the burners a lot more, your engine will speed up, but the propeller control unit initially will be waiting. It won't be governed by the propeller control unit. All we're doing is we're speeding the engine up. Okay. Then at a certain point, the propeller control unit will then take over and say, okay, now we need to adjust the propeller, or I don't need to adjust the propeller. It just depends on what power setting we've got. So the engine and propeller will then increase RPM. Okay. The movement of the power lever, continues with what's called dead movement. But this time, the PCU will control the RPM at a fixed level. So PCU is sensing the speed of engine. The PCU will only allow the propeller to spin at a certain speed. Doesn't matter how fast the engine's going, the PCU is governed by itself. So you can put the engine to totally flat out, but if it's too fast, the propeller control unit will switch the angle of attack of the blade to set to the maximum level. Hence, we've got a dead movement. So we might move the throttle up to maybe 90%, and up to 100%, you get more engine power, but the propeller is not. It's saying, nope, that's how far much an angle of attack is. I'm sensing the engine speed. I don't want the propeller going any faster than that because that's the maximum limit I'm allowed to do it technically. Okay, so we get what's called a little bit of dead movement. Fuel flow increases, the propeller blades will coarsen off to maintain the fixed RPM, because if they don't coarsen off, in other words, coarsen off means we increase the angle of attack, then the propeller will get too fast. So the propeller needs to increase the angle of attack to maintain the load on the engine. In other words, just a bit of resistance going through the air sideways. Next stage is for the power lever to now contact the valve. So remember in the PCU, the valve goes up and down. With the flyweights, remember the flyweights I spoke about last week? Okay, which move the valve up or move the valve down against the spring pressure. Well, the power lever will now contact the PCU and select a higher RPM. So if it goes a higher RPM, it's going to push the valve down until the final stage of movement where the power lever pushes the valve down, which decreases the angle of attack of the propeller, which allows the propeller to go faster. And therefore selecting a much finer pitch for takeoff. Because on a controllable propeller, we want a finer pitch of takeoff for takeoff, strangely enough. And then once we get the forward speed, the aircraft's matching the angle of attack, we can then coarsen up the blade so we don't allow the propeller to go too fast. And then we get to cruise ability, such like. Okay, so all right. So operation, a simplified single power lever system with positions. We'll put it down up in a minute. Positions A to D. You've got them in your book there, the bottom of page 39, but I will put it up in the diagrams. From A to D, A being at the lowest position, D being at the highest position. So minimum power to max power. Okay, and representing the full range of pitch control. So there you go. So we're starting down here, and then eventually we'll go up to D. So we're going to see what happens at each position. Okay, so minimum to maximum. The lever is at position A, the lowest point. Stationary aircraft on the ground and engine at idle, just ticking over basically. Speed at the fuel flow, your fuel control unit, is insufficient, so it's not enough to obtain the RPM selected at the PCU. So the PCU will only operate at a certain RPM. Well, idle, well, it's not a very fast engine, so it's not worried. PCU is basically just having a little nap at the moment. It's waiting until the engine speeds up before it takes over. Okay. So nothing really will happen. The engine's just warming up. Now we've got in here, we've got a linkage. You can see that where the position A is, we're at idle. Okay, it's connected to the fuel control unit, so it can speed up the engine. And then with a calibrated control and levers, we've also got the PCU connection. So you can see when we start moving this lever up, that this green lever will go forward. And then at a certain point, it will also start to move the PCU. But at the moment, we're at idle. We're not at the maximum stop on the fuel control unit, and we're not at the maximum stop on the PCU. So we call that PCU under speed. The PCU isn't doing anything at the moment. It's just the engine ticking over, as we say, sitting at idle. So the governor slide valve is under speed condition. Propeller is a fine pitch against the ground fine stops, which we spoke about last week. Propeller behaves like a fixed pitch propeller. RPM varies with fuel flow. Okay, as in the engine RPM. So then we start moving the operation. So when the lever is moved from position A, we move it up a little bit to B. We can now see that due to the angle here, the green rod here has moved forward. The little stop is now touching the fuel control unit, maximum stop, which will then make this one start to move. Not quite yet, but it's getting ready to move this other stop along here. Okay. No effect on the speed control spring at PCU yet, but it's ready to move because we have the stop is now going to move this yellow sleeve here, or slide, which will then move this slide up to the PCU. But still, again, quite at this moment, not quite moving the PCU, but getting ready to. Pitch is still fully fine. We've still got nice high power torque there, all is good. And the RPM increases with the fuel flow to the FCU. In other words, all we're doing from A to B, we're increasing the fuel to the engine. The engine's going faster, but at the same time, the PCU is still not controlling yet. It's still just doing its thing. It's like a fixed pitch propeller. So RPM increases with fuel flow to from the FCU to the engine. So the engine RPM will increase. On to the next stage. Centrifugal force releases the ground fine pitch stop. So as the engine is getting faster, we're still in a fine pitch. Those weights that lock in the control now disengage. That allows the propeller to slide forward a little bit and go into the flight fine position off ground fine. So position B, control slide allows oil pressure to move. The piston, if you remember, go back to the ground fine stop. Propeller moves off the ground fine stop into minimum constant speed. Now the PCU is controlling. Okay, this part here will have moved a little bit. Okay. Now note there is minimum constant speed is the minimum RPM selected by the PCU, which now allows rapid acceleration. This is all done by designers. The governors will be preset. You can adjust the governors to alter it again through wear and tear. Again, you'd have to follow your manufacturer's books for how much you like to do that, should there be a bit of wear. But again, as an engineer, when you're setting this up on the ground, you'll be checking the RPM when the PCU starts to control. So then we move from position B to C, and the speed is now selected on the PCU control spring. The PCU is governing speed, and as fuel flow increases, the blade angle increases to absorb the initial power. In other words, yes, the engine's getting faster, but now the PCU is in control. So to maintain that speed, it now needs to increase the angle of attack to put an extra load on the engine just to control the maximum speed of that propeller. Because if we didn't, the propeller would just go faster and faster and faster, and then we could get too fast. Okay, so we need to increase the load by increasing the angle of attack to put more load on the propeller. Okay, so as you see there, the maximum stop is on the fuel control unit. The PCU is now moving because we've moved that slide along as we move forward. Okay, so it's moving the PCU control as well. Then finally, we go from C to D to maximum stop on your power lever. You can now see we're also at the maximum stop on the controlling PCU. So greater RPM increases is required as a fuel steady increase for takeoff power. Forward speed increases. Okay, so actual aircraft goes faster, and the flight fine stop engages if fitted, if you have one. So remember, the flight find stop will pop out. So when we go to the minimum angle of attack, it will stay there until we need to come back into feather or shut down. PC reduces the blade angle to obtain the required RPM. Okay. Until flight situation changes. So typically the power lever will schedule fuel from idle to takeoff range by positioning the operating lever on the fuel control unit, or commonly known as the FCU. When a rear order selection is made from idle to reverse, so if you've got one lever which does your engine and does the control linkage to the PCU, but it can also come back away and go past idle, down, go to reverse thrust, we can go from an angle of positive 20 degrees to an angle of roughly about minus 20 degrees. Okay, so rearward selection, so you come down to idle, you've gone through a gate, and the power lever schedules not only fuel but also the blade angle. And it's worth making a note of those angles there. Okay, plus 20 degrees or positive 20 degrees to negative 20 degrees. And we call that thrust reverse range the beta range. We'll cover that again just shortly. So that's your power lever for a single lever, usually with a fixed turbine type engine. Okay, and fixed turbine being mechanically coupled. Again, we'll cover all fixed turbines and free turbines in Module 15 as well. So you've sort of jumped ahead to go back the way. So by the time you come to do Module 15, you can tell now about fixed turbines and free turbines. Okay, any questions on that part? There we go. Last bit is called beta or ground operating range. Now we can only select that obviously when the power lever comes back to idle, because there's no point in changing to a negative angle attack when you're flying at 200 miles an hour. Things will just start breaking and coming off. So we can only do that when we're on the ground and when we're at idle. Okay. So remember, the reverse thrust range is called beta range. And usually on the control quadrant, where your power lever is back to idle, there'll be like a sectioned area of maybe yellow and black sort of markings to let you know you are in the beta range. Okay. We'll just check there. I think it's Sanjeev. That's right. Okay. So moving on to dual lever controls. Now basically it's the same thing as a single lever, but we're just splitting up to two controls, one for the engine and one for the actual propeller control unit, your PCU. Used on turboprop engines with a free turbine. So just remember, normally a single lever is a fixed turbine engine, where dual levers are normally fitted to free turbines. Okay, now again, just to let you know again, free turbine is not mechanically coupled with an integral parts of the engine. It is a gas from the HP turbine, which turns the turbine of the shaft, which is connected to your propeller. So there's no mechanical gearings. It's just purely the gas coming out the internal part of the engine, which spins the turbine of the shaft of the propeller. Yes, the propeller will have a gearbox in the front for reduction gearing, but there's no mechanical couplings. So you could spin the propeller by hand and you will not turn the engine. But if you spin the propeller on a fixed turbine, you will start spinning the gearbox by hand. Okay. But again, we'll cover all that more in depth on 15. So just be aware then. So just to recap, as I say, single lever, fixed turbines, dual lever, free turbines normally. Now, one of these is your power lever, like we just spoke about. So basically, the power lever, I said, spins the engine up, supplies more fuel, to the engine to get the RPM, and then through that linkage we showed you in the previous slides, is also connected to the power control unit. This time, though, we've got a separate lever, hence the dual controls. Okay, so one lever is purely for the engine, and one lever is purely for the propeller control unit. Beta control, again, by moving the power lever through a gate into the beta range, just like the single one. A control unit on reduction gear will select oil pressure to find the blade below the flight fine position. Now, flight fine was the minimum angle of attack for a positive thrust. This time we're going to a negative thrust into what's called the ground fine position. Now, the degree of fining, often reversed, is also governed by the position of the power lever in your reverse thrust or your beta range. It's still the same as a single lever, but plus 20, minus 20. Okay. Now, some power levers, just an example on the aircraft, the ATP aircraft, have rollover levers. So instead of just bringing the lever back, and then going through a little mechanical gate, we've actually got a lever on a lever. So it's a double one. So basically, we can only bring that lever back and then grab the other lever in front of it and then pull it over the lever, and that's called a rollover lever. Now this lever is connected directly to the propeller control unit, the PCU, and selects required RPM by applying or releasing pressure to the governor control spring, just like a normal control. It operates when the propeller is in the normal constant speed range, but does not influence the propeller blade angle. Okay, while the propeller is operating through the beta range. So it'll do the power, as in the engine power, but it won't affect the actual propeller blade. Feathering and shut off, again, is selected by moving this control fully rearward. So this time, it's the propeller control lever that's going to do the feathering and etc. And there we go. This is an example of an ATP aircraft. Okay, there's your power levers for your engine, and just in front of these on a hinge, you'll see the power rollover levers. Okay, now it's these levers here. When you bring these levers back to idle, so move from this position to this position, once these are back at idle, then through mechanical linkage, you can now roll these levers up and over above these ones. Okay, and that way you can get reverse thrust into your beta range. Once you're in reverse thrust, you can actually push the whole lever assembly forward up to a certain percentage, usually about 50%. So an example there, a turboprop aircraft. So remember, a turboprop is a jet engine with a propeller stuck on the front. Again, whether a fixed turbine or free turbine, with a dual control unit, it's usually a free turbine type. Now, turboprops are constant speed engines because they operate through the operational cycle at pretty much 100% RPM. So pretty much a full power, and it's a propeller control unit that will maintain, increase or decrease the angle of attack. So to hold RPM constant, the fuel control adjusts the fuel flow in relation to the engine load. Okay. So when idling, the RPM remains high, but the propeller pitch is reduced until it's almost flat, so it produces very little thrust and requires minimum fuel flow. Now it's very, very fine position. Mechanical controlled engines normally use two engine controls on the cockpit quadrant, the power lever and the speed, or sometimes they call it condition lever. The power lever relates to the throttle of a reciprocating engine. In other words, another name for a reciprocating engine is a piston engine, but it also gives the pilot control over the propeller during ground operation. It affects the fuel flow, torque, and EGT. EGT is exhaust gas temperature. We need to know exhaust gas temperature so we don't overheat the engine. If the EGT gauge is getting very hot, the engine should sense that and reduce the fuel flow if it's automatic, or by the pilot, simply bring the throttle back. Okay, so one of the crucial indications you'll be watching a cockpit, you're doing runs, etc., is your EGT gauge, exhaust gas temperature. Now, usually there's four positions. Okay, so you have reverse, classified as REV. You have ground idle, or commonly known as GI. Flight idle, FI, and maximum, just shortened to max. So that's the usual positions. Reverse, ground idle, flight idle, and max. I like those ones. Let's see where we are. Okay. Speed or condition lever, again, primarily controls the engine RPM, so that's its main job, is the engine RPM. And some installation, it will also act as a manual feather and emergency cut-off lever as well, depending on the aircraft type. And this condition lever uses three positions. So therefore, emergency shut-off, RPM, and high RPM, nice and easy. Now, you won't have covered FADEC yet, although you work in some aircraft, you've maybe come across FADEC. We covered FADEC in Mod 15, but FADEC is the brains of an engine. It's a computer that controls the engine, okay? stands for Full Authority Digital Engine Control. So a FADEC controlled engine, there's a handling difference we have to look at. So we've got mechanical linkage type, governors, FADEC does it electronically. Now the condition lever no longer controls the propeller governor, as the task is calculated by basically a computer instead of mechanical. Okay. Depending on the position of the power lever, other aircraft system inputs and the flight phase. So it's constantly looking. It's far more efficient than still mechanical. So we can look at a few different bits and bobs. So typical range and stops. You've got your pitch range in flight, available pitch range on the ground. There's certain parts on the ground we don't need. Okay. And you've got your approximate takeoff angle and cruise angle. Again, the FADEC will be looking at all of this. This is an example, so don't worry too much about that. It's just giving an example of typical range and stops. Okay, positions of the propeller. Which again, we covered a bit of this last Friday. Your ground find stop, your flight find, pitch stop, etc. Now each propeller pitch control indicating system is designed and constructed to minimise development of any unsafe condition and basically give the pilot a clear and accurate indication of the propeller, what's performance, how it's working, where it is, again, during all operating conditions, whether it's at ground idle, whether it's maximum, cruise, takeoff, etc. So again, all working well. Now, loss of normal propeller operation or pitch control, strange enough, will cause a hazardous situation, overspeed of the propeller under intended operating conditions. So if you lose control, pitch control, we've got to react quickly, and depending if you've got one or two engines or more, then we'll make it far more harder to work out with. So a couple of things to look at. We've got three things. Each pitch control system that is within the propeller that uses engine oil for feathering must incorporate a means of override or bypass. Just in case something goes wrong, we can override that bypass. Normally operative hydraulic system components so as to allow feathering if these components fail or malfunction. It's okay having an automatic system, but if that automatic system fails, then we need to be able to manually control that. Each propeller approved for installation on a turboprop engine must incorporate provision for an indicator when the propeller blade angle is below the flight low pitch position. So again, we need to know if there's something going on there. Remember, I spoke about the hunting back and forward when the pitch stop has not quite worked. We might have an oil leak, so again, that could affect the pitch control. So we need an indicator to give us a warning that something's wrong. And the provision must directly sense the blade position and be arranged to cause an indicator to indicate the blade angle is below the flight line low pitch position before the blade moves below the flight low pitch stop. So in other words, we need the indications to let the pilot know, especially before he takes off, right, are my blades at the correct angle? If I get a light coming up and says, wait a minute, that's below flight fine, what's going on here? Something's not quite right. That prevents it from taking off, hopefully. Something simple though, quick correction, and it could be okay. So various forms of flight deck instrumentation are used to display performance of both the engine and propeller. So as a pilot, as an engineer, if you're doing ground runs, you're watching things like RPM, you're watching EGT, you're watching fuel flow, you're looking for lights coming on, lights going off. Some of you might be involved with ground runs already. You become a chameleon. You've got eyes going all everywhere, watching all the gauges, watching all the lights. You're listening for beeps and bops going on. But once you get experience in becoming a ground runner, as the pilots do as well, it comes second nature. Certainly when I used to work on jet aircraft, the fighter aircraft, we've got lots and lots of lights, lots and lots of gauges to look at, all very quickly. And it's up to you to decide within fractions of a second if everything's going right or if it's going to go wrong, okay? But again, it comes to experience and training. So yeah, definitely engine RPM, engine power, torque, have got enough power to take off. Engine manifold pressure, vibration, yeah, especially in propeller aircraft, vibration. Is it in the critical range? Have you left the RPM in the red zone when you shouldn't be in the red zone? Fuel flow, we need to know fuel flow. And the flight beta range, the normal flight position, your angle of attack, and your beta range angle of attack. RPM manifold pressure for piston engines. An aircraft with a piston engine and a fixed pitch propeller usually uses the tachometer. And a tachometer is just an RPM gauge to indicate throttle setting. With the RPM increasing, and as the throttle is advanced, and decreasing as the throttle is retarded. Now it's lessened off. A constant speed system uses a manifold pressure gauge, something known as a MAP gauge, and that indicates the throttle setting, and the tachometer is used to indicate the setting of the propeller control. Manifold pressure, if that gets too much, we need to decrease that, okay, and we'll slow the engine down. However, there's some interaction between propeller control and the manifold pressure gauge when changing RPM and holding the throttle setting fixed. Now, you go through more on piston engine in module 16 if you do module 16, but basically you can set power of the speed of the engine and the position of the throttle of the propeller. If you get that wrong, you can actually put too much pressure with the engine and potentially blow the engine up. So you have to match the power to the torque settings very, very carefully and very, very smoothly. Throttle body directly controls horsepower. So with a fixed throttle setting and horsepower output, the engine is constant. So a little example here. For instance, assume the engine is producing, come back in there. Assume the engine is producing 200 horsepower at 23 inches of pressure. Your MAP gauge, your manifold pressure gauge, is in inches of pressure. Okay, and the RPM is at 2,300 RPM. Okay, so we've got 200 brake horsepower at 2,300 RPM. If the propeller control is advanced to 2,400, so we've increased the engine RPM, okay, we're going to increase manifold pressure. So we need to do something about that. The manifold pressure must then decrease to the same lower value, for example, 22 inches, to agree with what's called the Planck formula. Now, we'll come on to what's called the Planck formula in a minute. So basically, if we increase RPM, we need to reduce the manifold pressure, because if the manifold pressure goes up in line with the RPM, there's a potential it could get too much. So we need to match one against the other. Likewise, if we bring the RPM down, we need to increase the manifold pressure. This is on piston engines only, okay? So we'll come on to what's called the Planck formula. So therefore, if the RPM is reduced to 2,200, like we said there, we need to increase the manifold pressure. That keeps the power within the engine available. So the example, we can see that when RPM is adjusted, a change in manifold pressure will occur. If we don't change it, then we'll either lose power or we increase too much power. Now, the amount of change will vary with different engines and obviously varying situations. It says that it should be noted that it's possible to damage the engine if the manifold pressure is too high for a given RPM setting. We can sort of deal with low manifold pressure, but if we go too high, we can certainly blow up, and especially when you get involved with turbochargers and superchargers. But don't worry about that for a moment. Always refer to aircraft performance charts and operating manual before operating an engine. Now, things that can affect that on the day if you're doing a ground run on an engine is the temperature of the day. So you've got thick, dry, cool air, or a very hot day, which could affect manifold pressure as well. So with a fixed propeller control setting, the manifold pressure can be changed with the throttle. The RPM, however, will remain constant because the governor will adjust the blade angle, like we saw before, to maintain the RPM. The caution there is when changing engine power settings, take care not to damage the engine by creating too high a manifold pressure for a given RPM. So as you're watching the gauges, you're watching your RPM gauges, you're also watching your manifold gauge, and make sure it is within its maximum range. Power to be increased, it's to best increase the RPM to the desired setting, then advance the throttle to desired manifold pressure. So you need power lever, then advance the throttle to desired manifold. In decreasing power, pull the throttle back till the manifold pressure is about 1 inch below the desired setting. And then propeller control can be reduced with a rise in manifold pressure of about 1 inch, resulting of the piston engine Planck formula, which we're going to come on to shortly. So the Planck formula refers to the formula to calculate horsepower. And what does Planck stand for? Right. Well, horsepower, this is what you want to highlight. Horsepower equals P multiplied by L multiplied by A multiplied by N multiplied by K, all over 33,000. 33,000 means for the moment, you cover that in module 16. What does the letter stand for? P is indicated mean effective pressure. L is the length of the stroke. In other words, how far up and down the piston moves up and down. A is the area of the piston head in square inches, so basically how round that piston is. And N is the number of strokes per minute. And K is the number of cylinders, so it's a twin cylinder, 3 cylinders, 4, 5, 6, whatever it is. Okay, that's what Planck stands for. Just be aware of the formula. Okay, we'll do a little calculation with it, but just be aware of the numbers and what PLANK stands for. When we do module 16, we go into Planck, Planck, and a few other different variations. Okay, but for the moment, all you need to know is this. Okay, RPM, manifold pressure, piston engine. Look at the first two. So look, we've got throttle set, propeller control increased, horsepower remains unchanged, manifold pressure is decreased, RPM is increased, and propeller is in the fine position. Propeller in course position, throttle set, and propeller control decreased, horsepower remains unchanged. However, manifold pressure is increased, but RPM is decreased. So basically, whatever RPM does, the manifold pressure should do the opposite. Okay. Propeller control set and throttle increased. So your propeller angle is set. Horsepower in this case is increased. Propeller to course. Manifold pressure increased. RPM is set. And the same for the last one. Propeller control set and throttle increased. Horsepower is decreased this time. Manifold pressure decreased. RPM unchanged. Propeller is fine. And at the end there it says comparison of the change in manifold pressure and RPM change in propeller control setting and throttle settings. It's worth maybe having a little read through. Probably put a line through the top there. So you split these two up and you split these two up. So the first two is the throttle set. The second two is the propeller control set. So that's the difference. Okay. So maybe worth just splitting it up in half. So you can see what happens when the throttle set, what happens when propeller control is increased, and when propeller control is decreased for these two. And then we look at the propeller control set for both of these. It's when the throttle is increased and when the throttle is decreased, and what happens to both of those. Okay. You might or might not get a question on that. It's one of those ones you're not expected to remember a table, but certainly what potentially could happen with the piston engine if we change one of those ones. Okay. All right. I'll just go for a break and we'll finish this bit off. In fact, no, that's probably a good point to finish. I'll leave that for the moment. What time now? 10:15 now. So let's go for the first break of the day. Okay. And we'll come back in about 20 minutes. All right. Okay, so see you in about 20 minutes, guys.
Right.
Hey, folks. Back again.
No,
All happy? It's the start of the week. Everybody still happy? Everybody good? Everybody healthy? Good. Is it nice and hot out there? It's very cold here.
Very cold here.
What's the temperature at the moment? I think we've got about 8 degrees here at the moment. The sun is out, but it's very, very cold. We've got you can just see some snow in the back hills. We had frost this morning. Too cold, too cold. Okay, right. Let's move on to the next part.
On mute karo mai disturb bhayirahcha.
We're going to move on to feather and unfeather. We'll look at the technical aspects of it, how it moves and back and forward, how we can, and a bit of recap of what we've done already. Okay, so in terms of feathering is, oh, something else coming out. Number 16. Parts of feathering is that when an engine stops in flight again, propeller would continue to turn due to the forward speed of the aircraft. So if you were to blow on a blade, it's going to spin round and spin round. So we put it into the feather position in line with the airflow, and that stops the engine from getting worse. So we don't want the engine to windmill intentionally. Sometimes we do. We might want to restart an engine. We might have shut, let's say, with a 4-engine aircraft, we might shut the outside engines down because we only did 2, and the inside maybe rotating. We can put it into the fine position, do windmill, and then start an engine, but that's on purpose. But if we've got a failure of an engine, we certainly do not want the engine to keep turning, so we'll put the blades into the feather position. All right. Again, just to recap, there's a picture of the blades. As you can see, the leading edge are facing into the airflow. So it will slowly move. You'll get a little bit of movement, especially when the aircraft's turning or whatever like that. But it certainly won't be spinning really, really fast. That's the main thing. It won't be windmilling. So it ends up two effects. It would also increase the drag on the aircraft if the propeller was spinning. It'd be act like a big circular disc. That's going to cause a lot of drag. And if in a twin-engine aircraft, you've got one engine causing drag, it's going to try and turn the aircraft one direction as well, which again could cause problems. Likewise, you maybe lost oil in your engine system, and if you've got the engine turning round, especially in a fixed turbine, it would certainly be spinning the engine, no oil, again, cause more damage to the engine than is necessary. So we'll look at feathering on a single acting propeller. I mean by single acting, again, before it was a big spring one side and we have oil pressure the other side. So as long as we've got oil pressure in there, which is pushing against the spring to a finer position and it's controllable, then everything's all good. But should we lose the oil pressure, then the big spring takes over, pushes the piston forward and puts it into the feather position. So that's the movement of the control lever achieved by moving the RPM lever back to the limit of its travel, back to idle, which opens up an oil way. So we're using oil pressure to help, basically hydraulics. We're going back to hydraulics, using engine oil as hydraulic fluid, which will, in the CSU, and operate the feathering lever until it lifts a slide valve independently of your RPM selecting mechanism and allows oil to propeller to drain back the engine. So in other words, we're draining the oil pressure off the front of the piston in the control mechanism. So the spring pressure takes over and puts it into the feather position. All right. So there we go. There's a basic setup. You've got your power control lever, which is on a rack and pinion. So a little gear there, which will move this valve up and down. Again, there's your center flying weights, which are normally working as normal. You'll have some sort of induction gearing, and then your valve. So the more that valve moves up or down, again, will allow the oil to flow and go drain back to the engine. So if that opens up, if it's in a low position, we can't feather, but if it's in an open position, we can certainly push down and drain oil back to the propeller, back to the engine, sorry, not the propeller. An accumulator, well, what was an accumulator for? Anybody remember? Got an unfeathering accumulator. So what would that be for? What does accumulator do again? Anybody?
It stores pressure.
Yeah, it stores pressure. So we can actually use this as an unfeathering mechanism. So if we don't have engine pressure, we could have oil pressure already trapped in there and enough pressure in there to actually move it back into the unfeathered position. Okay. It might be an accumulator or it could be an electrical oil pump. It depends on the type of engine you've got fitted. So unfeathering a single acting one. So to unfeather, the RPM lever is moved into the constant speed range, somewhere above idle. That lowers the control valve, and the unfeathering switch is pressed. That releases oil from the accumulator or the feathering pump. Go back to that diagram there. So unfeathering button, yeah, we're in the normal range. You have the lever, so that allows the pressure to go in into the valve and unfeather it. Okay. Again, it could be an accumulator that's got pressure in there, or it's some sort of pump, depending on the engine type. Now, action commences unfeathering, and once the propeller starts to windmill, the normal oil supply completes operation. Okay. So we have a lot of stored bit of energy there, either by storing the oil pressure or by using some sort of pump. So, then a double acting propeller, oil is then directed to course pitch and feather. So again, you've got your max and min control lever. This is just a slightly more complicated version of your PCU CSU you've seen before. You've still got a valve that moves up and down, but you've also got a valve within a valve, if that makes sense. So you've got this little valve here, you've got a feather control spring, which will bring up the main one. Now again, you've still got your flyweights depending on the speed of engine, but initially, this little valve here, now I'll try and change the colour on this one next time. There's a little yellow valve just going around outside here. Now that's inside the big valve here, this big one here. You can just about see where my red laser dot is there. It's underneath, it hooks in underneath the main valve. So if I move that feather control, it lifts the little yellow one, which then lifts the big yellow one, if that makes sense. Okay. Again, if that lifts up, it will then move the oil back from course back to the return, etc. And otherwise, at the moment, as you can see here, we are locked off. So at the moment, we'll be in hydraulic lock states. But we can actually, by lifting that up, can open the oil line, okay, fill a pump and put it back into whatever position, in this case, the course position. Put it all together, we go back to what we did on Friday with your ground fine pinch stop and also the flight fine pinch stop, remember? So we've got oil supply, nothing at the moment, we've got oil supply pushing this piston across, which is allowing the flight fine position to be locked in position. Okay, so we can't go to fine pitch at the moment. Throttle is closed to idle. You pull the RPM lever back to minimum, release the control lockout, and place the lever in the feather position. The action will control or pull the control lever upwards, which allows the oil to drain away from the rear of the piston and opening delivery of the oil to the front of the piston. So go back to the diagram there. So basically, when you move that up, as you can see that position there, the oil drains from here. That moves, allows oil pressure to build in here, pushes the oil back, pushes the piston back, we should say, which pushes it into a feather position. Okay. Remember the difference between a double acting and a single acting. When the single acting went back away, it went to fine. The double acting, it does the opposite, just because it can. It goes back to the course position. Okay, just to confuse things. Okay, so the throttle back to idle, pull the RPM lever back to minimum, release control lockout, place lever in the feather position, as it says already, and action will pull the control valve upwards, allows oil to drain away, so pushing oil to the front of the piston, and so on. Now, governor oil pressure will now be delivered to the front of the piston, but as the blade's coursing, the engine's obviously going to slow down because you're increasing the angle of attack, which is putting more load on the engine. All right, so that will reduce. So if you're slowing the engine down, therefore the oil supply will not be as much as well. Okay. Additional oil supply is now required to turn the blades to the feather position. So additional supply comes from your feathering pump, so your individual pump, which is operated by pressing the feathering or unfeathering button to start the feathering pump itself. So by coursing the blades, yes, we're going to course the blades, but we're going to slow the engine down. So you need this extra pump just to help us give the extra supply that we need. It's like a booster pump. So I was then pumped to the front of the piston and turn the blades to the fully feathered position. Oil supply comes from an oil tank, which is a reservoir of oil, usually by the engine's main lubrication system. So actually take a tapping of oil from the main lubrication system. When the blades are in fully feathered position, oil pressure builds up in the delivery line, which will then operate what's called a PCOS or POCOS, which is a pressure operated cutout switch. Okay, and when a certain pressure builds up, that cutout switch will engage and de-energizes the fairing pump. So we only need the fairing pump until it actually does its job. We don't need the pump running all the time. So when it gets to a certain amount of pressure within that piston, pressure builds up in the line, that opens a little micro switch and will automatically shut off the feathering pump. Okay, so this will go from course to feather. So the piston in this case, we're in course position-ish at the moment, and we're going to go all the way back into the fully feathered position. Don't worry about the centrifugal weights at the moment, but look at the position of the valve. All right, so at the moment, we've got oil pressure going through and then pushing on the piston to move the piston back away. All right, here's your POCOS switch. Okay, so that's waiting to be activated once the pressure builds up enough. There's your supply of engine oil, and there's your additional feathering pump. There's your normal oil pump. We just need the additional pump to give us that extra bit of oomph to get the oil going through. Okay, so let's have a look what's coming next. We'll push the RPM lever to min position through any lockout gate and then forward into the maximum position. This action will push the control valve downwards and allows the oil at the front of the piston to drain off. Therefore, by operating the feathering, unfeathering button, oil will be supplied by the feathering pump to the rear of the piston, rotating the blades, and this time into the normal pitch condition. This time, we're going back away. We're going forward. We're going to push the piston forward, represented by the high pressure here. And this time, you see the oil pressure line has switched round. Instead of there, it's now coming this way, which is going behind the piston, which is moving the piston forward. Okay, that's going to define position, excuse me. At the moment, there's your fairing button. Fairing pump activating as normal. Slide valve goes moved down. And say we've moved the position of the lever from minimum to maximum. Okay. Auto feather, an engine developing normal power should only occur if a failure would cause the propeller to auto coarsen whilst ground running, and the engine was developing its normal power for throttle setting. It might try and overheat because it's putting a lot of strain on there. Overheating will not normally be serious provided the propeller automatically moves right through the fair position without a pause. If it stops there, then we're in sort of trouble. Or your HP cock has been moved to the fuel off or fair position before the temperature has reached critical temperature. So it can go wrong. You just got to be able to react to it quickly enough. Automatic fairing a single or double engine propeller will normally activate whenever an engine failure is detected by the torque measuring system. So the torque measuring system is also sensing the torque from the system. Basically, we get a drop in torque. There's usually no auto fairing on single engine aircraft. Okay, why do you think that might be? So in twin engine aircraft, multiple engine, but in single engine aircraft, why do you think we don't want an auto fairing system? Does anybody have an idea?
No lift.
On one engine only. We've got an engine at the front, but we don't want an auto fairing system. If you've got one engine and it fails, what have you turned your aircraft into?
Glider.
A glider, yeah. Now, a glider with a big heavy engine in it, it's going to come down very, very fast, isn't it? If we put the blades into feather position, well, that aircraft's going to come really fast. We need something to help it slow down. So by not having a feathering system, auto feathering system, it will stay in sort of a finest pitch. Okay. Now that'll windmill, which in this case is actually good for a single engine because it will help slow the aircraft down. So it gives the pilot more chance to maybe try and find somewhere to land, you know, without obviously disastrous consequences. So we can actually use this case for a single engine only, using the propeller as a windbreak. It gives the pilot more controllability. Otherwise, they're just coming down like a 0 knots. Okay. Typical exam question sort of thing could be there. They might ask you what type of system or when would an auto fairing not be fitted to a single, twin, or quadruple engine system, single engine only. Okay. Twin engine we can live with. If it does, we need an auto fairing system because we don't want to drag the aircraft around, especially on a double engine aircraft. But set in a single engine aircraft, the engine's at the front, could be at the back. We can use that broken engine as a windbreak, which is actually beneficial to give the pilot more control. So it's the only time there's no auto fairing system will be on a single engine aircraft. Okay, worth highlighting that in your books. HP cock is usually automatically turned off when the auto feather is initiated. Water methanol supply to a fit engine is also automatically shut off. We don't want that extra power going into the engine. It's just going to go bang in the wrong way. So we don't need the extra augmentation of, especially water methanol, when the engine's not working. On twin or multi-engine aircraft, the other engine's auto fairing its isolated. So if you have a failure on one engine, it goes auto feather, that's great, keeps the engine feather, but we don't want the good engine or good engines to go to auto feather as well. So the system will automatically isolate the other engines. Now, if you lose the other engines for some reason, well, you just got to start praying, I think. You know, you come down a safe field somewhere. But certainly you don't want to have an auto fairing system activate on a good engine. Okay, it's down to manual. So single engine, no auto fairing system. On multiple engine aircraft, the auto fairing system will be isolated from the good engines. Only the bad engine will have the auto fairing system initially. Just gives the pilot some sort of chance to sort himself out. So automatic fairing single active propeller. Oil pressure will be directed away from the front of the piston. Okay, which is a fine pitch, because remember the oil pressure is trying to push the piston back away to fine. But if we lose oil pressure, then the big spring is going to push the piston forward, allow the fairing spring to act very quickly. There's a lot of pressure on that spring, and put it from the feather through course pitch. You will have a manual override switch, which is usually available for the pilot to select fairing manually. Basically, drain the oil away from the front of the piston. On a double acting propeller, when the HP cock is open position or lockout, and the throttle set in the cruise to takeoff range. If then the top pressure falls below, an example here is 50 psi, excuse me, the following will occur. Control side lift piston solenoid will be energized. So it senses that pressure drop. It will give a signal to the solenoid, also electrical solenoid, which will allow delivery of governor pump pressure to be delivered to the valve lift position, the piston, sorry, which raises the control valve up to accept the coarse pitch oil. In other words, it's going to put oil to the front of the piston and push it back away. Okay, remember, double acting do the opposite from single acting. Feathering relay will be energized. It allows the battery to feed the feathering pump, which will supply the coarse pitch oil. Because remember, the engine's slowing down, we get extra oil, so we activate the feathering pump just to help boost the oil supply. Excuse me, that's important. Okay, so an automatic fine double acting relay. Okay, so there's your POCO switch. Okay, hocus pocus as we call it. There's your feathering pump. This is the electrical diagram, what's going on. It's got a low torque switch, throttle switch, and your high pressure shutter valve switch as well, all micro switches. So if one of those engages, you have a ground test switch to make sure the circuit's working. All right, and then also when it all kicks in, you've got a relay, and it also isolates your other engine's auto feather system. Okay, so just in case the feather system is activated on the broken engine, it will also isolate the auto feathering system as well. Okay, on the good engines. So typical operation of thrust reverse propellers. Propellers kit of thrust reverse use a removable ground fine pitch stop, which allows the propeller to move through the fine pitch to a negative pitch because it's going thrust reverse under certain conditions. You need to have a fail-safe, as you'll learn about this in module 15, gas turbines as well. A thrust fail-safe is designed to ensure this facility cannot be selected during flight. There's no point in having a thrust reverse facility as you're flying normally, because things will just start getting ripped off the aircraft when they shouldn't be. Okay, slow down far too quick. Electric control is usually achieved by lockout levers or switches mounted on the throttle landing gear, and definitely on your weight on wheel switch. The weight on wheel micro switch activates and also disengages certain systems around the aircraft, which are only applicable when the aircraft is on the ground. So again, when you want a thrust reverse system, you only want it when you're on the ground. Okay. Throttle levers closed to reverse date and position, reverse selected, so on. The weight on wheel switch, etc. Pitch stop withdrawal solenoid will direct oil pressure to withdraw your fine pitch stop. So you need to move that piston back to drop down the little lock so you can move the propeller into thrust reverse negative position. Pitch change piston will move the reverse pitch stop and held in position by hydraulic pressure. Reverse selected, you can then use your thrust reverse as required. You're getting an indication, obviously. We need to know that indication has moved, so you get a little light in the cockpit. And the blade's position in reverse pitch, usually provided by hub-mounted switches with a limited warning light. You don't need to know the range. That'll be up to the pilot to move that, but you just need to know that, yes, I've gone past the flight fine pitch stop, so I'm in my beta range, my thrust reverse range. Positive blade angle is reselected by moving the throttles into normal. So you're in the beta range at the moment, but you come back up to just before idle, click through into idle. That will then move your blades back into the normal range. The fine pitch stop will return back to normal because the oil pressure will drained off, allowing the piston to turn back to normal position under spring pressure, and the blade moves past the normal stop. And then you can go back to your normal flight position. Typical beta range, thrust reverse, gives the pilot control of the blade angle and engine power operating on the ground. Okay, so during flight, the throttles and power levers operate in a gated coordinate and cannot be closed below the flight gate. So we can't physically do first thrust in flight, no sense to anyway. On the ground, the levers are pulled into beta range, engaged in a cam in the CSU, which raises or lowers the governor valve, altering your blade angle accordingly for the thrust reverse. Control the propeller blade angle in reverse, again through your beta valve, which is normally built into the base of the governor. And the propeller is reversed by manually repositioning the cockpit control to cause the beta valve to supply oil from the governor pump to the propeller. Now, it can be external, can be internal. a propeller change pitch mechanism, position feedback, which includes a beta slip ring, okay, so we can get the electrical power through a slip ring, and a carbon block assembly, which communicates propeller blade angle position back to the beta valve. And diagrams in your book, I think it's on. Page one there. Yeah, page 59. That's the same diagram you've got there. Okay, so you see the control rods. There's your main valve, and it's not the clearest diagram, but it's just basically showing you where everything is. Shut-off lock solenoid, and then your hydraulic low pitch adjustment and so on. Okay, and then there's obviously your control governor as well. And that's what it looks like when it's all together. Just again, these sort of diagrams you might come across in your manuals, and trying to find part numbers and bits and pieces and that sort of thing. So a typical example, about to move the propeller blades into a negative, your beta range. Angle permits either partial or full reversing of thrust on landing. Now that significantly decreases the total land distance. That saves you having to push your brakes on all the time. And depending on which throttle is available, depends on the runway and depends on the aircraft. So we've got an example of a single-acting propeller in reverse thrust. So during the flight range, the beta valve is held in the open condition, which allows the oil to the PCU slide valve to fully control the propeller. Normal flight range movement of the pitch change piston is transmitted via the beta feedback rods. We need feedback rods because that's the ones that actually move it, but we need to know what's happening as well. And they're in conjunction with some springs. It does not influence the beta valve position as it remains in the open condition as long as you're in the reverse thrust beta condition. Selection operation thrust reverse is inhibited, fail-safe until the following criteria are met. So, just to recap, you must be idle or minimum of idle. Depending on the type of system you've got, you might have the role of a lever type. Aircraft speed and attitude are correct. In other words, you're on the ground and you're going slow enough. We don't want to put the reverse thrust on straight away because that could be too fast and that could end up pitching the aircraft into the wheel. So weight and wheel switch, yes, that's a micro switch, or aircraft discrete as we call them. And your flight, so ground fine pitch stops are removed. You can't go into thrust reverse until they are removed. The engine will be idle, the propeller will be on the low pitch stop. So when the aircraft lands, there will be some method of removing that low pitch stop and the ground fine stop when selecting thrust reverse. But briefly mentioned it already. Okay, so depending on the system, there's propeller there, obviously course and fine, you can see the connecting rod. Okay, now depending on where this piston, this part here is, all right, there's your spring. Depending on what the pressure in the system is, we'll move it back and forward. Depending on your control and depending on speed, etc., will depend what you can actually do with reverse thrust. So the engine will be idle, the propeller will be in a low stop position, and when the aircraft lands, again, we'll figure that out. Okay, in reverse mode operation, the PCU or CSU. Okay, which one was which? Which engine had the PCU? Was it piston or gas turbine?
Gas turbine propeller.
Yeah, gas turbine, yeah. It's a pity they didn't make it PCU for piston because that make it nice and easy. They both look the same, just slightly different, but just again, just the design's been different. Okay, operates in underspeed condition to act strictly as a source of pressurized oil with attempting to control RPM and propeller pitch. So when the power lever is moved from the flight idle position, so keep going back the way into your reverse range, it will now move so that the pitch change piston and beta feedback rods will take up the free movement of the springs. Usually via a control rod through a beta cam box, so you've got a cam type shape thing there, assembly linked to the engine pilot control. The full movement of the beta feedback rods is then transmitted to the beta valve, which moves it to the rear. And that causes the beta valve to close off the oil pressure to your PCU slide valve control. Stops oil going back to PCU slide valve control, prevents further firing off and overspeed until the correct idle speed and everything else is accomplished. Basically, the selection of thrust reverse should be rapid and smooth to prevent the risk of propeller overspeed. So basically, when you bring your power lever back, it's going to fine off. If you sit there as you're going through into thrust reverse, that could be really spin up really quickly. So you want to come back to idle and go straight back into thrust reverse, obviously if you go into thrust reverse. And then you can use the normal power. If you sort of hesitate there's a chance you could overspeed the engine, but you don't want to do that. So nice, smooth, rapid acceleration. Bring it down straight through the gate, and all is good. All right. And there's a bit of feedback rods. You see the spring there. Okay, now there'll be a bit of slack plate to start with, but once you get the pressure, then you've got your pilot input, yeah, which will push. You've got the carbon slip rings, so they're slipping within a ring, which they can push on the rods, and that will send, so that gives feedback to there. Now, attached to there is your beta valve, so depending what position that's in, or the oil pressure to and from the actual position for your piston. So when all the criteria is obtained, fuel selection and thrust reverse repositions the beta valve so that oil from, again, your CSU or your PCU is routed around the beta valve to the propeller pitch change mechanism. So basically, go back to that diagram. So once that's moved, we allow oil, that'll push up, that'll go down, and then push the oil to the front of the piston, move that back. Now, as that moves back, it will also move the beta valve rods as well, the feedback rods, and that gives a sense of what's happening here as well. Okay. So there it has moved. So if we go to that previous diagram, you can see that it's blocking off the supply from your PCU at the moment. Okay, so make a note of that one. As it builds up, you now see that has moved forward a little bit. So it's now got oil supply going round and going through into the piston. All right, and then we get a balance until it moves. Depending on what the pilot's doing, moves throttle. The more that moves, the more pressure builds up until it's sorted. As oil, the pitch change piston will decrease the blade angle. The propeller enters the below idle position, and to fuel thrust reverse, which will bring the beta rod indicator if fitted. So basically, the springs will take over, put it to fuel reverse position, because remember it's going forward this time. That will then move your feedback rods, and then that will affect your control. The pitch spring piston is fully forward. The beta feedback rods via your carbon blocks and slip ring will hold the beta valve in place. Okay, and that will allow further movement rearwards of the power lever, which will increase engine power. N is speed, and G stands for generator. We speak about turboprops as a generator engine. Although it's a gas turbine, we call them NG. N is also speed. So when you come to do module 15, anything with the N in front of it means speed. If I was to say to you N1, N2, or NL, NH, that would be LP speed and HP speed. In this case, we're looking at NG, okay, gas generator speed. You might come across one shortly called NF. NF is the speed of the free turbine. Okay, so you'll learn more about annotations as we do module 15, etc. So example there, to 85% to 80% through additional linkage between the beta cam box lever and assembly and fuel control unit. In fuel reverse, the blade angle will be roughly negative 15 degrees, okay, thereabouts. Well, you're going to think, well, wait a minute, negative 15 degrees, that's a stall, you know, because positive 15 is a bit of stall, negative, very, very close to 15%, 15 degrees there. But again, you're not on full engine power either. All right, so thrust reverse selection, you can see now, fully locked in thrust reverse position. All right, negative angle of attack. So instead of going forward like that, it's got a negative angle of attack, fully forward, and there we go. All right, so that's a sort of setup for there. Just be aware of angles, thrust reverse, that if you have a failed engine on a multi-engine aircraft, the other system will be inhibited, so it can't work on that. And then we'll look at some other bits as well. So we can also fit brakes, and it sounds weird, fit brakes to the engine. And this is for a typical turboprop engine. Now the brake system on this works exactly the same, but pretty much the same as brakes on your car or motorbike. Okay, so a propeller brake, that stops the propeller from spinning, but allows us to actually start the engine. You'll have this on turboprop engines, on free turbines, and also helicopters. We don't need the big rotor spinning round, we just want the engine. So due to freewheeling characteristics of turbine engines, especially those on free turbine type, in part propeller can revolve at some speed in relatively light winds. So we can have the engine switched off, and especially on a free turbine, fixed turbines can do it as well, but they've got the resistance of the gearbox. When a free turbine, it can spin very, very fast on its own. So we can actually put a brake on the shaft here. Now, because inertia is throwing propeller, engine shut down, the engine and the propeller will continue to rate for some time. So if it's quite a windy day, you're packing a wind, you shut the engine down, propeller keeps spinning, spinning, spinning. It might take a long time to slow down. So propellers and passengers on the passenger access side of the aircraft can be at risk of disembarking. Yeah, we don't want passengers coming out and then walking into propellers. That's going to make a bit of a mess. Okay, we don't like that. So to cut down the freewheel time and the run down time engine, we can apply these brakes once all your indication cockpits are fine. The brake is usually hydraulic in operation, the aircraft's hydraulic system. Hydraulic, change that there. Brake is applied exactly the same as a car or motorbike. Okay, friction pads held in the caliper pistons are squeezed against the disc, which is bolted to the drive shaft of the engine. And you'll see a bigger version in a minute. But there's the drive shaft, there's a disc like a car or a bike, and there's your caliper with your brake pads in it. Friction produced will slow down rotation of the drive shaft and propeller, eventually bring it to a stop. Propeller brake lever control is usually fitted in the centre console in the flight deck, and is usually interconnect to the propeller brake lever with the high pressure fuel cock or HPSOV. That ensures that the fuel is selected off first before they put the brakes on. No point putting the brakes on when the engine's running because that's going to cause a lot of damage. So by having it interconnected with the throttle lever, fuel will be deselected. That means you shut the engine down, it will start to cool down, you can then put the brake on. So therefore it cannot be applied when the engine is running. If it does, something's wrong. Okay, so fail safe there. So due to the heat produced by friction in the pads, fusible plugs are also incorporated into the body of the brake unit. Okay, so just in case it overheats, on normal aircraft, some of the brake units on the main undercarriage on some of the bigger aircraft, they have fusible plugs as well, which will melt out should it overheat, and exactly the same for here as well. Plugs will melt if the temperature of the brake is excessive, and basically that releases the hydraulic pressure, basically with no brakes. Okay, now if that goes on a normal undercarriage or normal aircraft, well, that could be a bit awkward. On this one, the worst thing can happen is, okay, but it bleeds off the pressure, it'll just take a little while longer for the propeller to stop. When overheating the brake, manufacturers usually lay down a maximum engine speed at which the brake can apply. So you might switch the engine off and you'll be watching the RPM gauge come down, and then they'll say at a certain RPM, now you can apply the brake on. Okay. Should never be applied at higher speeds than those specified. So let the engine slow down till it's suitable speed, and then you can apply the brake. There's a bigger version. Okay, so there's a brake disc. Okay, attached to the shaft. There's your caliper, and inside here will be the pads. Okay, can't show it on this one, but there's a fusible plug. There's a hydraulic connection off to your hydraulic system, and there'll be a fusible plug around there as well. Propeller over speed, next one, is a condition of which the actual engine speed is higher than the designated engine RPM, as set on the propeller control by the pilot. So we've basically got an overspeed governor. Again, good old flyweights here. Again, set in position normally. Too much will fly out, move the valve up. We've got the same thing going on again. So I guess conditions prevented by overspeed governor, because the governor's in charge. A component used to control propeller RPM should a failure in the CSU or the PC occur is your overspeed governor. So just in case your CSU or PC fails, we do have a separate overspeed governor. There are no connections to this governor from the cockpit since its speed setting has been set by manufacturer or test bed. Go back to the diagram. You can see there's a spring here, a pre-tension spring. There's a little slot here. You can actually increase the tension or decrease the tension. So you can let this operate at a lower speed or a higher speed, depending on what's required. Again, when things vary, you can readjust it. But normally, it's preset rate, like a pressure relief valve. Connections. Normally, around about 2000 RPM, thereabouts, or 104% NF. And this is what I was on about. NF, speed of the turbine, free turbine. Okay. Most free turbines might be about 100, 101%. If it gets to 104%, well, that's 3 to 4% too much. So that overspeed governor will sense that speed because of the flyweights. They will come out, they will open the valve and release the pressure. Okay, so roughly about 2,800 RPM or 104 NF, speed of the free turbine. Usually located again on the reduction gearbox, overspeed governor can regulate the flow of oil to propel a servo piston with its own set of flyweights and a pilot valve. So should the CSU or PCU governor fail, overspeed unit senses that. So the PCU hasn't gone, it's gone cuckoo, it's gone broken. The governor says, wait a minute, this is not right. Let's open up. And that will allow oil to flow from the CSU or your PCU system, flow back to the reduction gear housing. And the governor will continue that to restrict the propeller RPM from increasing further. Okay, right, just before we go for a break, sure I covered that bit. Yeah, I'll just finish this bit off and we'll go for a break. So you've got an electrical test control. Normally it's just a mechanical preset and that's it. But because the mechanical overspeed governor is usually set to 4, maybe we're highlighting 4% above maximum RPM, it cannot be tested for correct operation during normal engine propel operations because we're not really going to get past that. So we need a way of pretending we've gone 104% or over 2000 RPM. Okay, because we don't want to get the engine at that speed because we're going to damage the engine. So what we've got, there's usually no mechanical controls for this type of governor. However, we will have an electrical solenoid mounted on the forward surface of the unit. This permits the governor to be tested for correct operation. It just lets us know that is working. So a test procedure does not guarantee that the governor will work when needed, but it does check roughly the approximate setting of the unit. So it's a bit of, well, how do you know it's working? Cross your fingers. Electrical test control. You have a switch on the pilot's panel. It will energize the solenoid. It allows oil to enter the upper housing of the unit and decrease the spring pressure on the flywheel assembly, so pretending that we're going to overspeed. RPM is increased and the propeller tachometer is observed. If the propeller RPM increases to the maximum permitted and remains there, although the engine RPM is still rising, then the overspeed governor is assumed to be tested and is controlling correct. So we press this button, you put your throttle up, and it should go to a maximum amount. When you keep going past it, nothing else happens, unless you take your finger off the button, obviously. When the switch is released, the oil is drained from unit and the speed tension is re-established at the manufacturer's test bed setting. And there it is there. Okay, there's your little test switch. Okay, so oil supply will energize it. That will move that up. That will allow oil to go in. That will move the valve up, pretending that the centrifugal flyweights have moved. They haven't. We just physically put some oil supply in there to test it. All right, and then that will drain off to the gearbox, so we can't go past the manufacturer setting. That's all it does. Okay, right, that leaves us ready for the FADEC side of things. So let's switch that now. 20 past 11, yeah, let's go for a 20-minute break. And we'll do a little bit of FADEC and then we'll go for lunch stroke tea afterwards. Okay, so see you in about 20 minutes, guys, okay? Any questions before we head off? Okay. Good. No. Still looking at blank screens. All your faces are round dots with initials in them. Okay, see you after tea break.
कति चाँडो ब्रेक हुन्छ यार
राम्रो नि मलाई निन्द्रा आयो झुपझुप भन्छ
सीट मेटल भनेर
We've got the coffees, we've got the teas.
Wheel सब पनि राम्रोसँग गरेको छैन सीट मेटल पनि गरेको छैन
All right, guys, we're ready to move on to section 8.
Yeah, welcome back.
Welcome back. Always good to be back. I'd rather be out in Nepal than here. That would be different. That would be far better. Hopefully sometime we will get back. Right, moving back to section 8, we're going to look at FADEC. Okay, full authority digital engine control. Nowadays, most modern aircraft will be used some sort of FADEC system, but it's a gas turbine engine, turboprop, whatever. Tends to be old FADEC. In my day, with the military aircraft, we use a thing called the DECU, basically the computer of the brains of the engine. FADEC controls everything. I've got a few bits and pieces that do little bits as well. So basically, the FADEC itself functions to limit control speed of propeller. Power turbine are as follows. The FADEC software adjusts propeller blade angle through the pitch control to your PCU, which will control the propeller, the power turbine speed. It does everything. It controls, it sends the signals. It also needs feedback. We call a FADEC a fully redundant system, closed loop system. Again, you'll do FADEC in module 15. Basically, send information out, receive information back, and it will check it against some data it has in its memory or ADC in an aircraft. Now, a hydraulic mechanical overspeed governor, so we've got mechanical override just in case, applies emergency protection if your propeller, your power turbine overspeed condition occurs. And so just in case we lose electrical power or whatever, we've still got the mechanical backup of a good old governor. The governor is always in charge. Even though the brains is electrically wise in charge, we've still got mechanical backup just in case. Okay. Power changes momentarily or if a failure occurs. Now, typical FADEC functions to limit control speed propeller per turbine as follows. If the propeller power turbine speed is more than the limit for the propeller governor, the FADEC software sends a signal that will decrease the fuel flow. It's saying, wait a minute, we're going too fast here, something's not going right, let's just bring the fuel back a bit. And then engine power level will be restored. FADEC has a microprocessor, independent overspeed protection to stop the flow of fuel. And it prevents an overspeed condition that can obviously cause damage to the engine. Digital propeller speed control, again, typically there are just a few turboprop engines equipped with digital speed control. It's still good old FADEC out there, but there are some newer versions in the system now. So system description, primary components of this type of system are, we've got pitch control unit, the PCU, the feathering pump, your overspeed governor, beta tubes, your feedback rods that we saw earlier. Okay. And system inputs are cockpit controls, condition lever, power lever, feather, unfeather switches, etc. Also got propeller speed probe and an auto thrust system and good old FADEC as well. During engine start sequence, when the condition, or shortened abbreviation for COND, is set to run, with the aircraft on the ground, the FADEC sets the system in the beta mode. In the beta mode, system changes the pitch of the propeller as a function of the power lever angle, or PLA for short. Beta feedback transducer, which is the sensor, sends data about the position of the beta tubes, in other words, the pitch of the propeller, back to the FADEC. So FADEC can say, right, okay, what angle are my propellers at the moment? So when the aircraft is in flight with the power lever between normal range or flight idle and maximum, the system controls the propeller in the constant speed mode. All we've looked at before is mechanical operation. We're just still doing the same thing, except this time it is the FADEC in charge. During landing, the FADEC sets the system in the beta mode when these conditions are correct. Again, like I saw before, the power lever is between flight idle and ground idle. The FADEC gets an aircraft on ground signal. That would be from your WOW switch, your weight on wheel switch. When the system is beta mode as well, the pitch of the propeller is related to the power lever angle. So when the power lever is set to reverse mode, system sets the propeller in the reverse pitch position. In that configuration, the system operates in the reverse governing mode and keeps the speed of the propeller between idle and minimum constant speed range RPM. System usually operates automatically in one of three modes: beta control mode, constant speed mode, and reverse governing mode. That's the three main modes. Again, that's on page 69, so it might be worth highlighting those ones. So automatically on those three modes there. So beta control mode, again, system only uses the beta mode during operation on the ground. There's no point in having it in the air because we're flying. FADEC controls the propeller control unit and sets the pitch, as we saw before, in relation to your PLA. And to keep the relation between pitch of propeller blades and the power lever angle correctly, the FADEC will monitor or continuously measures signals from the speed sensor of the engine. So you get a speed up probably from your NF, that sort of thing, or NG, depending on type. Normally the free turbine ones will be NF. Controls the servo valve in the propeller control unit, and therefore controls the flow of oil to the pitch change of the actual propeller. Therefore, in beta mode, the system does not use overspeed governor. The FADEC gives the propeller the overspeed protection. But likewise, if the FADEC fails, we've got the good old mechanical overspeed governor just in case. But in normal, good operation, the FADEC is the brains and is in charge of everything. So in beta control mode, to do this, the FADEC calculates the speed of the propeller with the signals from the MP sensor, a power turbine or a free turbine, might be NP, might be NF. Decrease the supply of fuel to the engine if the speed of the propeller gets to a set limit. So with the power lever between flight idle and maximum, the system goes into the constant speed mode. In that mode, the system sets the speed of the propeller at constant speed RPM. All this is saying is the FADEC's controlling everything. It will make sure it's set the correct mode, correct angle, and correct RPM. It controls the servo valve as normal. Propeller control to change the pitch and the speed appropriate. Okay. And again, measures the speed of the propeller. And we'll also compare the data if it gets just the servo valve as necessary. So there will be an onboard computer with reference data. The FADEC will check the reference data against the actual inputs that's physically happening there and then to the engine and the propeller. During operations, constant speed mode, when else the speed of the left hand and the right hand propeller is almost the same, the system goes into what's called synchronization mode. And if the speed of the propeller gets to more than 104% RPM, the good old overspeed governor kicks in and will take over. So the overall speed governor operates, it disconnects the supply valve from the governor assembly to the PCU and therefore changes the pitch engine or piston of the propeller. So with no supply of oil, pitch change position propeller, the counterweights move the propeller towards the course pitch position. Propeller blades move towards the course pitch position, the speed of the propeller decreases. Yeah, more angle, more pressure on the blade, that will reduce the speed of the engine. Reverse governor mode. Before the FADEC, we'll set the system into reverse mode. It needs to know a few things. Again, obviously crucial, it must be on the ground first, so it needs to get on-ground signal. The pitch of the propeller must be less than 18 degrees. Okay, again, maybe worth highlighting that one. The power lever must be in the reverse position or rev range. And first, when the conditions are correct, the FADEC sets the PCU to the beta mode range. PCU in beta mode, pitch of the propeller is set in relation to the pilot's throttle lever angle. Finally, the FADEC sets the PCU in reverse pitch mode. That's fine. Reverse pitch mode is set. The pitch change piston on the propeller moves quickly to the full reverse pitch position. We don't want it in a very fine position too long because it will overspeed. So in that configuration, the FADEC uses the same procedure to control the system, okay, as it does with the constant speed mode. So it's very, very similar. It's just waiting for the commands, waiting for the inputs, the sensors. It says, okay, once I'm in that range, I will then move it accordingly. Auto fairing mode. With the auto fairing function armed, the system automatically goes into the auto fairing mode immediately. The FADEC gets an engine failure signal. It uses two different parameters to find the failure of an engine. First one is the power plant, which is your engine natural airframe, is at a low power condition during the approach to an airfield or when the aircraft makes a landing. The FADEC uses the signal from the engine speed sensors. That would be NF for that one. The power plant is at high power condition. So when the aircraft is in the takeoff, the climb or cruise mode, the FADEC uses a signal from the engine torque meter pickup. So speed signal and your pickup signal. Low power condition, FADEC uses a signal from the engine speed sensor. Yeah. High power condition, again, uses a signal from the engine torque meter pickup. So complete the auto feather procedure. FADEC sends an auto feather inhibit signal to the feather of the opposite engine. Remember what I said before break there, that if we got an engine that's in problem, we have to shut down, it will go into auto feather mode, but we need to make sure we keep the good engine good. So it will disengage the auto feather system on that good engine. Okay, and the system automatically sets propeller to its fire position when the engine fire handle is also pulled. So say you have an engine fire, and you've pulled the engine fire handle above you, depending which one it is, it will automatically go into auto feather as well. That's part of the system. So there's quite a lot going on for that actual system. Signals from the engine fire handle go to the two channels of the fuel pump and the metering unit, what's called the fuel pump metering unit, or FPMU for short, just more abbreviations. And the two channels of fading out. I've mentioned already, again, we'll go more in depth in module 15, but FADECs have two channels, A and B. And just a bit of insight, A is the one that's normally operating all the time, and B is the one just there in case. They do alternate between startups, but normally B is the background, just keeping an eye on channel A, and should something go wrong, channel B will take over. The pilot won't know that, because it's all automatic, but there's two channels within a FADEC. Again, we'll go more into depth on module 15. So the signals to your fuel pump metering unit are for the engine shutdown procedure, which includes the propeller feathering procedure. Manual feather, like we saw before, manual feather function operates independently of the other functions. It's manual for a start. Because it operates independently, it will set the propeller in the feather position if selected by the pilot. So when the man feather or manual feather switch is pushed, it will operate the feathering pump. Gives a pressurized supply of oil that we saw earlier this morning to the oil system. The pressurized supply of oil from the feathering pump flows through the PCU, through the coarse pitch connection to the beta tubes, and to the pitch change piston of the propeller. A lot of P's there. Pressurized supply of oil is sufficient in all conditions to set the pitch change piston of propeller in its fully coarse position. Okay. And that is pretty much that for that one. Just double checking anything I want to highlight there. Yeah. There's nothing really drastically need to highlight that one. Just be aware of the terminologies. FADEC, auto feathering, manual feathering, a few other bits there. There's nothing really too drastic about it. Just remember, FADEC is the brains of the whole outfit. All right, will activate certain points. Main things, it needs to know what flying conditions it is. Is it on the ground? Have we got weight and wheels before anything else operates? And should all systems fail electronically by FADEC, we've got the good old governor, overspeed governor, which will take over just in case. Okay. All right, so that is chapter 1. Any questions on some of that stuff? Quite a lot to take in. Some is very similar. You'll probably starting to recognise some similar bits from part 1, even book 1, in fact. But just all we have instead of a mechanical process, we have FADEC, the digital brains looking after things. Okay. So briefly mentioned synchronization, and we're going to look at synchronizing and synchro phasing. Two sort of similar things, but to do with multi-engine aircraft. You might have heard this terminology before. Okay. So we'll do a little bit before lunch, and then we'll recap a little bit after lunch. So what is synchronizing and synchrophasing? Well, you've got these big spinny metal things on the front of the engine called propellers. They're flying through the air. They're getting this thumping effect, and they're quite propellers because a lot of vibration. So in the cockpit, we want it as quiet as possible and as vibration-free as possible. So interior noise and vibration in commercial aircraft is dominated by a propeller, what's called blade pass frequency, or BPF. And it's what's called low order harmonics. So harmonics have got quite a low frequency, similar to elephants. When they communicate, they've got a very low rumble, and certainly with the propeller aircraft, you get a sort of low rumble going on. And through time, that can be very disorientating to crew and passengers, etc. And also vibration to the engine and the aircraft can cause a few problems. Typical gas turbine engine blade pass frequencies range, and maybe worth to note here as well, between 60 to 120 hertz frequency. And passing control of these frequencies can be difficult due to the weight penalties. Yes, we can improve things by putting sound insulation and making things stronger and thicker. But again, that causes weight in the aircraft, which means more fuel, bigger engines, so you're counteracting. So there are a few techniques you can use to help it. Noise levels often exceed 100 decibels. Now that's okay for short periods, but if you're subject to 100 decibels all the time, sort of factory environment, that can cause permanent hearing damage, disorientation, and obviously just general uncomfortableness as well, and also damage to the aircraft. Not good at all. So most modern aircraft with 2 or more propellers now have what's called synchronization and synchrophasing. And we'll look at the 2 different types of systems. It's therefore believed that global reduction arises from the arrangement of the relative amplitudes of the fuselage vibration modes, in such a way that they couple less efficiently with interior cabin acoustic and floor vibration modes. So it's basically going to affect various parts of the aircraft. For example, it's known that noise generated by propellers is influenced by thrust and inflow distortion, and that cabin noise levels in propeller aircraft can be influenced by altitude and also airspeed. Altitude, where's the thickest air? Down below. So when the aircraft's spinning through thick air, you get a much more increased thump. Higher level, higher altitude, less air, less resistance, should be a lot smoother. Forward airspeed as well. Yeah, you're actually pushing through the air. As the propeller's cutting through, that can cause a lot of noise and vibration. So let's look at the synchronization system. Now, propeller synchronization, you think of synchronization, it means in line with, okay? So propeller synchronization system is used to set all governors at exactly the same RPM to help reduce excessive noise, vibration, and open fatigue, okay? So we're going to set the governors of both engines, say we take twin engine aircraft, for example, to be the same RPM, so in synchronization, hence why it's called synchronization. Now, synchronization may be used with governors having mechanical or electrical types. It just depends, but the principle is exactly the same on either system. Systems are used on both large and small piston and also turboprop aircraft. Basically, got a propeller on it, we'll use the same system. Normally used for all flight operations except for takeoff and landing. So highlight that one. When would it not be used? Takeoff and landing. Why? Well, you're taking off, you need high power, we can't get away from it. But when you're cruising, we certainly don't want the high vibration and high noise, etc. So we'll synchronize them normal flight, but we don't need it for takeoff. And your landing, well, your engine should be a reduced throttle setting anyway. Failure of the master engine would result in all engines trying to follow the master engine. What I mean by that is we'll set the master engine to an RPM, and the slave engines will then try and copy the master engine. Now, if the master engine fails, then the slaves will try and copy what's not there, and they'll end up going out of sync as well. So if a master engine fails, if it's a twin engine aircraft or 4 engine aircraft, the slave engines will try and copy what was the master one. Components. Master engine is used to establish RPM. So we're using the master one, and all the engines said they are called the slave engines, and they will adjust. So on a 4 engine aircraft, any engine can normally be selected. You can choose anyone to be the master, but normally on a twin engine aircraft, it's usually the inboard left engine. On a twin engine aircraft, it'd be the left-hand engine or port engine. If it's multiple aircraft engine, multi-engine on an aircraft like 4, it'd be the inboard left-hand first. So it's normally left-hand side is standard procedure. So some components you're going to have a control box for synchronization. You'll have the shafts, you have a trimmer, you have a pickup, you have a governor on the right. This is the right-hand engine, and this is the left-hand engine, which would be the master, and the slave on the right-hand side. You'll have a connection, so that's called pulse signal, the speed of this one will go to the signal box, and you'll have a speed of the master go to the signal box. Okay, and then the synchronized box will then adjust the slave to match the master. Okay. But if a tachometer system using an RPM gauge, a speed signal, voltage directed to a differential motor, compare the master engine RPM to the slave RPM. Okay, so it's always compared against the master engine. Therefore, the system voltage generated by the tachogeny system is used as a reference on a high voltage wins base. So the highest voltage is the winner, and the other one will match it. So if a frequency generator is used, the engine signals are sent to an electronic unit, which compares the frequencies this time and sends a corrected signal to the slave engine to then govern control mechanism. You either speed it up or slow it down. Now, the synchronization control box has a limited range of operation, and the slave engines must be, good to highlight here, must be within 100 RPM of the master for synchronization to occur. So if it's above 100 or below 100, we won't get synchronization at all. So it's got to be within about 100 RPM. A 4-engine aircraft system may include a master engine selector, so you can actually select 1, 2, 3 or 4, it's up to you, but normally left hand inboard, which allows the pilot to select the master engine to be used. Again, normally engine 2 or 3 in this case. That's how they're numbered. Usually things are numbered from left to right. So on this side, left-hand engine or left-hand wing would be 1, 2, 3, 4. So normally your master would be, in this case, inboard. On the left-hand wing would be number 2. And then the rest would all be slave engine. So 3 and 4 and 1 would be slave. But you could choose, it's up to you, you could choose any engine as you wish. But standard procedure normally is the left-hand inboard wing. Why? It just is. But you do have the option. Switch provide alternative master engine if the current master engine should become off. So say you lose engine power on this one breaks, then you can choose another engine to become the master. I think that's probably the last thing you're worrying about if you lose an engine. Normal ration slave engines are near the master engine, again within 100 RPM, when the synchronization system is switched on. Signal comparison from the master engine and the slave engine signals through the synchronization box cause the slave engine's governors to adjust the same RPM as the master engine. So that box will send a signal out and the governors will adjust and either speed up or slow down the slave engines accordingly to match the master engine. Tear noise and vibration can be a serious problem with propeller aircraft. Okay, so we'll look at what's called synchrophasing. So synchronization, it's just as it sounds in synchro, that all engines are going the same speed, the same RPM. Okay, and it makes control obviously easier as well. Instead of you've got 4 throttles in your cockpit and you're individually trying to move the RPMs, well, by using the synchronization box, that takes the load off the pilot as well. So synchronization or synchronizing all engines, same RPM within 100 RPM. Now we're going to look at what's called synchrophasing. That's to do with the angles of the blades as they're rotating compared to the master. So again, synchrophasing, that can cause tear noise, vibration, again, serious problem, not just discomfort of the pilot and crew, also vibration of the aircraft. Broadband noise inside any or many propeller airplanes is dominated by turbulent boundary layer air rather than propeller, particularly at higher flight speeds. Propeller location, again, significant factor in that, the 10 propeller noise levels in the cabin because of the strong directivity characteristics. So airplanes with a single tractor type of one we've got there, mounted in the nose of the airplane, usually have quite low levels of propeller noise in the cabin. Okay, not too bad. Yes, they're in front of the aircraft, but the propeller's further ahead. Okay, so it's not too bad. Multi-engines though, on the wing, well, the propellers are actually very close to the cockpit, aren't they? As it's spinning round. And have high cabin sound pressure levels in the vicinity of the plane of rotation. Right. Now, also, you can see here, this propeller's spinning anti-clockwise, and this propeller was probably spinning clockwise. So they're spinning together. Now, you imagine as propeller blade comes round to the cockpit there, you're getting a thump. If you get a thump that side and you get a thump that side, then if you all at the same time, that's going to double the size of that noise. Okay, so a massive sort of thump going on. So we can use this synchrophasing mechanism shortly. Pusher aircraft, engines at the back. Again, why make this? Why not? Are mounted after their cabin. Operating to disturb the airflow of field and propeller noise radiates forward. So although the engine's at the back, it's making the noise go forward and impinges on the airplane fuselage. You'll get a beat. Every time a propeller blade comes in, you get a beat, or a thump as I call it. And multi-engine airplanes, the propellers are not synchronized. So we need to get synchronization done, then we do the synchrophasing. So pressure cancellation augmentation due to phase difference between propellers can result in rapid spatial variations of interior sound and pressure levels. Imagine as propellers coming round, it's also pushing air towards the cockpit. So if you push at the same time, that's a lot of high pressure. again, that's a lot of problems. So we're going to put these propellers, although they're at the same speed, which we've done to synchronizing, we're now going to put the blades out of position slightly, so they're not both coming at the same time. All right, so generally accepted that propeller synchrophasing is a way of minimizing the noise and the vibration in most modern aircraft with 2 or more propellers now have the synchrophaser systems in them. Manual synchrophasing in flight is a refinement of synchronization and allows the pilot to set the blades of the slave engines a number of degrees in rotation behind the blades of the master engine, whilst still maintaining the same RPM. So let's think, for example, you've got 2 engines running, both at the same RPM, within 100 RPM to set them, so they're both spinning at the same time. We're happy with that. But what we're going to do is that's the master propeller there. We're going to put the slave propeller slightly back. So every time it spins, they won't be exactly at the same position. So this one will come round and that one will come round. That prevents them both propellers spinning at the same position at the same time. So in practically, what we call synchrophasing, we're actually putting the angle of the blades out of phase to the master, if that makes sense. Okay, just slightly behind the position of the blade. The main thing is though, the engines are set RPM correctly, we're just moving the blade angle, and not the pitch of the blade, the actual position of the blade as it rotates on the axis, slightly behind the master one. Okay. So let's have a look. So there's 0 phase angle. Okay, so again, that would be a master engine, this would be a slave one. Phase angle in this case, there's a master at 0. We've now moved the position of the blade at 20 degrees. And there's one at 48 degrees. So synchrophasing sets the blade angles of propellers at different angles and maintains the same RPM. Now we can control that in the cockpit. We can increase or decrease the angle as appropriate. Again, that's down to experience of the pilots, etc. Okay, and that's what we're trying to do there. So we won't have both the blades in line. The slave engine will be slightly behind the master one. So as this one's spinning around, so that one's spinning around there, by the time it gets to that position, that one's only about that position. So this one will go around past, so get a small thump, then that one will give a small thump. But you can imagine if they both came around together, that's a lot of pressure wave going in the same position. So that's why we synchrophase. But synchrophasing has only achieved limited success as a method of noise reduction. In practice, the mere possible reasons for this are twofold. Firstly, synchrophase angles of some aircraft may not be properly optimized. You can have a certain angle might be better than another angle, usually only within 5 degrees. So there's not much point there, is it? You're only 5 degrees out. Well, that's not much of an angle. Secondly, and perhaps most importantly, the fixed synchrophase angles found in most synchrophasers may be inadequate to cope with the changes in the noise and the vibration environment, usually brought about by different flight conditions. So from high altitude to thin air, come down to low altitude, thick air, cold days, hot days, will all affect the type of noise levels. Example we've got there is known as the noise generated by propellers. It's influenced by thrust and inflow distortion. Cabin noise levels, prop aircraft can be influenced by altitude and airspeed, like I saw before. So by looking at there, if we're using, there's a noise level peak that way, got airflow coming in. So without synchrophasing, the noise level is almost double without synchrophasing. With synchrophasing, sorry. So you can actually almost half it. With twin engine aircraft, you can almost half the amount of noise just by changing the angle the blade starts and stops from using synchrophasing. Typical system components, you have a pulse generator fitted to the same blade route of each propeller. We need to know, because we changed position, we won't be able to work at the angle correctly. So example, number 1 blade, the signals generated are used to ensure that all number 1 blades are in the same relative position at the same instant. Okay. So let's have a look. So your left-hand propeller and your right propeller. Okay. You have your governor for each engine. Then you have your prop synchrophaser switch. The little sensor on each one. All right. So you see at the moment the blades are in the same position. Pulse generator serves the same function as the tachogeny in the synchronization system that we saw before, but comparing the signals from the slave pulse generators in relation to master engine pulse, the mechanism will synchronize and synchronize the phase relationship of the slaves to the master engine. So it will set them initially both together. Okay, and Phase control unit receives the signals from the pulse generators, compares them to the master engine, and sends a correcting signal to the governors. All right. So your pulse generator replaces the tachogeny in this case, and will send the feedback. That adjusts control of the slave engines to establish the phase angle selected by the pilot. So you can actually turn a control and actually set the angle of the slave engines. So a propeller, the manual phase but control in the cockpit, control knob allows the pilot to set the phase angle, said already, which will give the minimum vibration. So if he's putting out of phase, still getting a bit of vibration, he can change the angle a bit more or increase it a bit more, depending on what he's feeling. And that's what it looks like there. So the synchrophaser light is sync, so get them in line position. Then you go to phase, so you can actually manually change it or indeed switch it off. It might be fine, you might not need it. Slaves are operating at nearly the same RPM. The system is switched on, so we're pretty much synchronizing first for the first part. Then we switch the synchrophaser on, and the slaves will synchronize with the master engine. Okay. Electronic unit will adjust the governors to set propellers at the phase angle set on the pilot's control panel. So depending on what angle he's got set on, it will then move the position of the blades accordingly. The pilot can vary the phase angle by rotating the control dial. And that will cause the electronic unit to readjust the governors, thus setting the new phase angle. Now we've got active synchrophasing. The active control of the synchrophase angles using feedback from cabin mounted microphones. In fact, what we'll do, what time for there? Let's have a look. If we go too far ahead. Okay, there. Too far before lunch. Oh no, we'll finish that. We'll finish that because we've got ice coming up next. Yeah, we'll finish this one, and then we'll go for lunch. Okay, so active synchrophasing. Now, for the manual synchrophase, this active one. The active control synchrophase angles using feedback from actually microphones within the cabin cockpit environment. So microphones and accelerometers, which give you vibration analysis, with appropriate adaptive optimization strategies, reduced cabin noise and vibration over a wider range of flight conditions. And what it is, say the pilot manually selecting it, these sensors will pick up the noise. They will say if it's in limits or out of limits, and then they will adjust the phase of the system automatically. Again, it takes it out of the pilot's hands. The problem with that is you're putting more systems on the cockpit, more systems in the aircraft, you're adding more weight. More weight, again, more fuel and so on, so more money. So active control using signal sources such as loudspeakers, shakers, or piezo films may ultimately provide greater reductions in cabin noise and vibration. Again, it comes down to good old cost. Complexity and weight. So there's pros and cons. Yes, it makes it a better system, but it comes down to money factors and cost and weight. Probably find it more in larger aircraft compared to smaller aircraft. Again, active synchrophasing offers a worthwhile noise and vibration reduction and a few penalties, which enhances the performance of other active noise control methods by minimizing the noise in the cabin. If you make that cabin more user-friendly, it takes the load off the pilot, navigators, etc., and makes the flight more enjoyable as well. Okay. So that was basically synchrophasing and synchronization. Synchronization, control of the RPM of the engines, they both match. Synchrophasing is we move the propeller blade out of alignment with the master, and that's controllable by the pilot. Okay. Active synchrophasing is a more expensive version by using speakers, microphones, piezoelectric vibration transducers, etc. Again, cost and that effect. Okay, thanks. I think that's a good point there. We'll stop and we'll start with propeller ice protection after food. Yeah? Well, happy to go and get some lunch and tea now.